Picture this. A tiny antimatter atom is tearing across a lab bench at nearly 100,000 miles an hour. Then, almost magically, it stops acting like a solid BB and starts rippling like a wave on a pond. Wild, right? Today, we're jumping right into that moment and asking a simple question. What on Earth, or maybe what off Earth, can that ripple tell us about gravity itself? Here's the scene. Our main character is called Positronium. Think of it as the Romeo and Juliet of physics. A positron, the antimatter twin of the electron, dancing with an ordinary electron. Romantic, but short-lived. Left to itself, this pair annihilates in a blink. So how do you record a love story that ends almost before it begins? First signpost, the positron parade. The researchers needed a whole crowd of identically prepared atoms streaming through their apparatus. Random directions? Different speeds? That would smear out the delicate wave pattern. So they built what's basically a particle traffic controller. Step 1. Spit out positrons. Step 2. Let each one snag an electron. Step 3. Filter that chaotic swarm so only the A-list atoms, same speed, same timing, get tickets to the experiment. Think of a marathon where only runners with identical stride and pace are allowed past the starting line. Second signpost, stretching the soap bubble. Even with the perfect runners, positronium normally disappears long before reaching the finish. The fix? A quick laser kick shoves each atom into a Rydberg state. Picture stretching a soap bubble without popping it. Now the positron and electron orbit farther apart, and the atom survives long enough to cross the lab. Instead of a nanosecond sprint, we get a short but manageable commute. Third signpost, the nano-picket fence. Next, the researchers aim this fragile beam at a nano-fabricated grating, an ultra-precise picket fence etched into a chip. But there's a twist. The ripples they care about, de Broglie wavelengths, are tens of picometers wide, way smaller than the micrometer-spaced slits. So no dramatic double-slit photo here. The interference shows up only as a faint, statistical nudge in where atoms land on the far detector. Let that sink in for a second. Fourth signpost, reading the ripples. A fancy detector waits on the other side, not just counting hits, but recording the exact landing spot of every single atom. Over hours, dot by dot, a map builds up. Finally, faint fringes appear, regions a bit richer in arrivals alternating with regions slightly poorer. The contrast is only about 15%, but that's enough. The pattern screams quantum interference. So if everything looks the same, what's the big deal? Well, sameness today opens the door to spotting tiny differences tomorrow. If a future, more sensitive version of this setup ever sees the pattern drift because of gravity or some hidden field, that wobble will stand out against a backdrop we already understand. Let's zoom out and imagine where this leads. Future vision, the quantum seismograph. Swap tectonic plates for interference fringes. Any tiny push, gravity, electromagnetic fields, maybe something more exotic, will make those fringes shift, tilt, or blur. Compare different atoms in the very same device. Regular hydrogen, positronium, maybe antihydrogen. If one pattern drifts while the others stay put, it's like two musical notes sliding out of tune. That off-key moment could signal brand new physics. Sound sci-fi? Remember, GPS and MRI started as lab curiosities. A positronium interferometer could one day calibrate satellite clocks, map space-time ripples, or probe dark energy. Not monster hunting, just better understanding what the room itself is made of. All right, time to land the plane. So here's what we covered today. 1. We met positronium, a fleeting atom that's half matter, half antimatter, then watched researchers whip it into a patient Rydberg state so it could survive the trip. 2. We followed that atom parade through a nano-fabricated picket fence and saw how a detector stitched together thousands of landings to reveal a faint but unmistakable interference pattern. 3. We learned that, for now, antimatter atoms surf the same quantum wave rules as everyday matter, which sets the stage for ultra-precise tests of gravity and new forces down the road. And here's the empowering part. When you hear the word antimatter, don't picture comic book explosions. Picture a ruler, a freakishly sensitive ruler humanity is just starting to use. Every fringe in that interference pattern is a tick mark. The better we read those ticks, the more clearly we can measure the universe. Before next week, try this. During your commute, cooking, or scrolling your phone, pause and imagine the hidden waves beneath every solid object. How does that shift your sense of reality? Pick one snap judgment you usually race through. Trap it, like the alpha collaboration traps antimatter. Then test whether it really holds up. Finally, tackle a familiar problem from a brand new angle. Change the metric you use, just as physicists swap experimental setups, and see what fresh possibilities surface. Do that, and you're thinking like a quantum experimenter. Thanks for listening. If you enjoyed this ripple through reality, share the episode, hit subscribe, and come back next time for more science you can feel. Until then, keep questioning the obvious, and keep your wave particle options open.